Okay, so we have chapter 4 with trigonometric functions. So first we're going to start out with if we have degrees and we need to transfer it to radians, or we have radians and we're going to convert it to degrees. So say we have 270 degrees, we will multiply that by pi over 180. You can also do 2 pi over 360, whichever one you prefer, and that will equal 3 pi over 2. And then say you want to get, you have radians and you want to get degrees, which are the equations right here, so you'll need to know those for the exam. You'll have 3 pi over 2, and then you multiply that by 180 degrees divided by pi. The pi's will obviously cancel out in that case, and then the degrees will cancel out in this one, so then you'll get 270 degrees again. So that's just how they will cancel out, and you can get from degrees to radians or radians to degrees. Another thing with angles that we need to know is arc length. So if you have like a piece of pizza that has a degree of 60 degrees, so you'll just multiply the 60 degrees, which you have to turn into radians. So you'll multiply that by pi over 180, which equals pi over 3. And then you just multiply the radians times the radius as shown in the equation. And then you'll get 2 pi. And that's just the arc length of that case. You can start figuring out basic triangles, which, so the basic triangles we'll need to know are the 45, and then the 30 and 60. So this will be root 3, this is 2, and this is 1, and on the 45, 90, this is 1, and this is 1, and then this is root 2. And that's just a basic thing you'll need to know for the exam. So for an example of this, we will say that if you have cosine of, so say you have cosine theta equals 4 over 7, you want to do a triangle, which will, so cosine is adjacent over hypotenuse. So this will be, say this is the acute, so it's going to be the acute angle. So this is going to be the theta. So you have 7, 4, and then you need to find the third leg, which will be root 33. And so to find just sine, cosine, cosecant, secant, which sine is going to just be opposite over hypotenuse, so root 33 over 7, cosecant, which is already given, and then tan is going to be opposite over adjacent. So tan of theta, remember to put theta, sorry, is going to be root 33 over 4. And then once you have that, you'll know the opposite. So cosecant is the opposite of sine. So cosecant is going to equal 7 over root 33 over 7. Because when you have a square root in the denominator, you want to bring it to the top so it's not in there. The opposite of cosine, which is going to be the hypotenuse over the adjacent leg, is going to be secant, which is just 7 over 4, so that one's pretty easy. And then cotan is the opposite of tangent, and that will just equal 4 root 33 over 33, which is, this is supposed to be 33. Sorry, this is 33 right here, because you have to cancel out this, and so it'll be like 7 over root 33, and then you multiply by root 33 again, and then they just cancel out, obviously, and you'll do that on the same one. So that's just how you find the basic 6 trigonometric functions. So another thing that you'll see on the test most likely is if they give you a point on a graph. So say you have the point 4 over, or 4, 7. So you go over 4, up 7. This is 4, 7. And one mistake a lot of people make is attaching to the y-axis, but don't ever do that. You want to attach to the x-axis. So this will be your right angle. You go up. So this is 4, this is 7, and then you want to use the 4 squared plus 7 squared equals c squared, obviously, to find the third leg, which the third leg in this case equals root 65. And then once you find that, they'll ask for the trigonometric functions again. So you find sine of theta, which the theta will they can say like acute angle or whatever angle that they would please, but this case it's mostly right off of the in the center right here. So to find sine of theta, you'll do opposite over hypotenuse, which once again you want to get the root out of the denominator, so it'll be 7 root 65 over 65. And then you find the cosine of theta equals adjacent over hypotenuse. So that will be, again, 4 root 65 over 65. Tan will be of theta equals opposite over hypotenuse. So that will be 7 over 4. And then the cosecant of theta, which is obviously the opposite of sine, equals root 65 over 7. And then secant of theta equals root 65 over 4. And then cotan is going to be the opposite once again, so you'll just flip these around, and it will be the adjacent over the hypotenuse, or the opposite side. So that's just how you'll find that angle.
Go.
Another part of the section is going to be sine and cosine curves. So a basic sine curve, you have it with a period of 2 pi, and then an amplitude of 1 So the sine, you will have it right here, and the basic parent function just goes right here, and right here. That's just the basic one of sine. And then the basic cosine parent function, you have the amplitude of 1 again, and a period of 2 pi. And it starts at 1, goes down, and then goes like that, just like in one loop. So that's your basic cosine. And
2 on the bottom.
oh, that's supposed to be 1, sorry. That's your basic parent functions. So the equation for this is a sine of b times x minus h plus k. So this is going to be the amplitude, which in the parent function is 1. And then the b is that helps you find the period and also the frequency. And then h is going to be the horizontal shift, and k will be the vertical transition, either up or down. So an example that we have right here is going to be y equals 4 sine of 8x minus 2. So the amplitude given is 4, so amplitude equals 4. The horizontal shift is going to be 2, because you look right here to make sure that it's always negative. That's going to be a positive shift, or if it's positive, then it's going to be to the left. So the horizontal shift is 2. And then the period, the equation for a period is p equals 2 pi over the absolute value of b. And so we have b right here, so the period will just equal 2 pi over 8, which obviously equals 1 pi over 4. And so that's just how you will find the period and the amplitude and the shift to give your basic function. And so here we'll draw the graph. So Ms. Gassick would like you to do 2, most of the time do 2 of the periods to show in your graph. So we'll have 4 here, and then -4, and then 1, 2, 3, 4. So this will be 2. So the horizontal shift is over 2. And then we'll make it so that the period is going to be pi over 4. So that means that this whole thing will be pi over 4. So I like to do dots at the amplitude in between. This is going to be a sine curve, so we'll have the amplitude here, and then another dot here, another dot here, here, up at 4 again, once again, and then another one here. And that will just help you draw your curve easier. And then this right here is going to be your period, and that equals pi over 4. So that would just be how you draw an equation if you're given it. So that's how you do that one.
Today's installment, the second half of chapter 4, it refers mostly to the graphs of the basic trigonometric functions learned in the first half of the chapter. So to start with, here's the tangent function, written as tan x, and here's how it appears graphically. Its zeros are at every integer multiple of pi, and its asymptotes, such as right here, and right here, for example, are at odd integer multiples of pi over 2. And like it, the cotangent function looks very similar. It's like what would happen if you reflected the tangent function in a mirror through the y-axis and shifted it the same shift that a sine is to a cosine, 1/2 pi on the x. So it ends up looking like this. It ends up looking like this. This is cotangent x, and you can see by its definition, because cotangent x is defined as cosine x over sine x, that you can start to see why the zeros and the asymptotes are where they are. So whenever a cosine x is 0, such as at pi over 2 and 3 pi over 2, negative pi over 2, and negative 3 pi over 2, then cotangent x will equal 0 as well. And wherever sine x equals 0, there will be an asymptote, such as right here and here, at 0, and then at pi, negative pi, and so on. Secant function is the opposite of the cosine function, and so if you start with the cosine as it's drawn here, then secant looks like this. And because cosecant is the inverse function of sine, then the function shape of cosecant is exactly the same, but it's just shifted 1/2 pi to the right. Another topic in the second half of chapter 4 is that of composite functions. One of the interesting features of it is the concept of damped oscillation, which essentially means that as the function progresses, the amplitude gets progressively smaller or bigger, or reaches a point at which it begins to get bigger and then smaller. So an example of damped oscillation would be like the function y equals x squared cosine x, and the dampening factor in this case is x squared. You can always spot damped oscillation by looking for anything in the a value of the original function that will alter the amplitude progressively. And so for this, these two parabolas would be this x squared and then negative x squared would be the lines around which cosine x gets damped. And so the function itself would come to look something like this. And so on. And you can see that as you get closer and closer to 0, the function y equals x squared cosine x, the y value for it, gets progressively smaller and smaller, and it goes increasingly large as you go to positive infinity or negative infinity. But always the key in looking for damped oscillation is whether there is a variable in the coefficient of the cosine or sine part of the function. Another thing to note about composite functions using sinusoidal properties such as sine x and cosine x is that some of them are periodic. In fact, most of the ones referred to will be periodic, and periodic can be anything that repeats itself, such as this, for example. If it continues to do that over a set amount of values on the x-axis and just keeps going at that period, then it's a periodic function, regardless of what it looks like or how wildly the amplitude varies. But a sinusoidal function always looks like a sinusoid, like a sine or cosine, and will always just be going up and down simply like this with a set period without doing anything unusual in between periods. It always looks consistently like a wave that's just simply going up and down. Inverses of the trigonometric functions are interesting because they have to have their domains and ranges restricted in order to keep them functions. So for example, arc sine, that is inverse sine, has to be within the boundaries of pi over 2, negative pi over 2, 1, and negative 1, because these would be the domain and range of, well, 1 and negative 1 would be the range of the sine function, and now they're the domain of arc sine. And similarly with pi over 2 and negative pi over 2, except these had to be restricted in order to make arc sine an actual function that looks like this. And looks like this. And once again, the restriction on the domain is necessary in order to keep it to be a function. And likewise, arc tangent has to be restricted also at pi over 2 and negative pi over 2, and continues between them as such. A useful way to go about using inverse trigonometric functions is to set up a triangle such as this, so that given a problem such as arc cosine 1/2, you would see theta and the ratios associated with 1/2, and knowing that this is the ratio of a 30, 60, 90 triangle, then you can see right here that theta equals 60 degrees. Angle of elevation is the angle someone would be looking up from straight ahead. This angle right here. And angle of depression is always the angle that someone would be looking down from straight ahead at where they are standing. It's never here and never here. Finally, as an example from section 4.8, is problem number 5 in the text, which refers to a tower, which would be, this would be the tower, and a wire that comes down from the tower and is 5 feet away at the ground and forms an angle of 80 degrees from the ground. And the question asks you to find the height of the tower, which I'll call H, and the length of the wire, which I'll call L. And so the length of the wire, L, is what divides 5 feet in the ratio cosine 80, because cosine is adjacent over hypotenuse. And so if you actually calculate that out, solving for L, 5 feet divided by cosine 80 equals 28.8. So that would be the length of the wire. And similarly, solving for the height would be done by saying sine of 80 equals h over the hypotenuse value, which we calculated as 28.8. And so h, after having solved for it, comes out to equal 28.4 feet, that is.